Hi guys, we're going to be talking about the introduction to the Electron cloud, Electron configuration today. So what you need to know is this. Our question is, where are the electrons? That's what we're going to be finding out. We're going to be finding out a lot about where the electrons are. And just like this picture, you know, the honest answer for most of the questions that we're asking today is that we're really not sure. We don't know exactly where the electrons are because we either know where they are the split second we took the picture, but as soon as we take that picture, they're no longer there, or we know what they're doing. We can't know both. This is known as Heisenberg's uncertainty principle. So why can't we know exactly where? Because they're really fast and they're tiny, and really fast and tiny isn't, I mean, think about football pictures. You get somebody running and it looks like a blur unless you got a really good camera. But as soon as you take the picture, that football player's not there anymore. So here comes question number 1. Okay, so what do we know about where electrons are? We know that the atom is very organized. And this thing called an electron cloud, even though it's a cloud and we can't know specifically, we do know that all electrons are placed in orbitals. All right, and orbitals by definition are three-dimensional regions where an electron has a 90% probability. That means it's a 10% probability that it's not there. But you and I have to figure out what these orbitals are, how many there are, how many electrons can go in each one. But right this very second, we're just really interested in figuring out what orbitals are. All right, so orbitals are not orbits. Please get that out of your head. Yes, I will do my hand in circles like it's going round and round and round, simply because it's the easiest way to describe something that's tiny and moving around, but it's not going around in an orbit. It's not a path, okay? It's not a path. It's not like the planets. The easiest way to consider what the orbitals are is their addresses, all right? And you can have a specific address or you can have a very generalized address. The orbital by itself is a relatively general address. 90% of the chance of finding the electrons there. But just like this house that's being shown, do you know what rooms anybody's in right this very second? And the answer is no. You got a 90% chance, especially if it's at midnight, that everybody's there sleeping. That's about as best you can do. All right, so there are 4 orbital shapes: S, P, D, and F. And we're going to spend a lot of time talking about these orbital shapes, but right this very second, I just need us to be able to understand that they are there. All right? Your goal is to be able to see these. They are 3-dimensional shapes, what the last slide said. That means S, which is a sphere. It's round. It's like a ball. P is a peanut. And we're not talking about a flat peanut. We're talking about a 3-dimensional peanut. It's got height, it's got width, it's got depth. D is referred to as a double daisy, and F is the flower. All right, the periodic table is divided into 4 sections or blocks, each one of which identifies the shape in which the electrons in that block are being placed. It's a real easy thing, and getting to know this portion of the periodic table is massive. All right, so if you look here at this periodic table, you will see where each of the blocks are. You see the tall blocks are the S and the P. They're referred to as the representative elements because those, the S electrons and the P electrons, are your valence electrons. The D's and F's are not. They're considered transition and heavy metals, but the ones that you and I are going to start with, and the ones that you dealt with in physical science, are the S and the P blocks. They're the ones that you talk about most of all. All right, so the periodic table is, and I know you guys know this already, so this will be really quick and fast, or it should be quick and fast. We know we have rows. Those are referred to as periods. We also have columns. I'm not worried about the columns today. I'm only worried about the rows. All right, so what you need to know about every row is that the electrons placed in the outermost energy level, which is known as the valence shell, is identifiable by the row number. So the valence shell for row number 1 says that there's only one circle. Everybody in row number 2 has its valence electrons, the electrons in the outermost level, in level 2. Okay? Now you know how many elements there are, at least through the first 3 rows, based on how many boxes there are. Now, after you get past row 3, I'm sorry, things begin to get crazy. We're not going to do that part today. Okay, so just another picture here, all the elements in the second row. The first row's filled up. Can't fill up the second until the first one's got stuff in it. But we're filling up the second row. All right, now there's a rule that we're going to talk about again at the very, very end. It's known as off-bows, and that basically says you can't put anything in 2 before the 1s are filled. Anything can't go into 3 until the 2s are filled. And again, once we get past row 3, things get kind of crazy. All right? Okay, I know you guys again know this. But I'm going to ask the question anyway. You know, what do we call these guys in the outermost level? They're known as valence electrons. Please also know you cannot have more than 8 valence electrons. And if you go back to that periodic table, count how many columns there are in the S's. There are 2. Count how many columns there are in the P section. There are 6. 2 plus 6 is 8. The only electrons ever in the valence shell are going to be referred to as your representative ones are the S's and your P's. All right. I'm not going to worry about how many there are in every single level because this gets to be very confusing. But what you need to know is that with every level of the periodic table, until we run out of electrons for right now, you can put more and more electrons in each and every energy level. All right, just a couple of other things to know for right this very second. I already said it, but you need to understand it goes in the S's first. After that, you go into the P's. After that, you go into the D's and the F's, but they are never on the outside. Right, so here again is that statement. The S and P orbitals are the only orbitals that are filled in the valence shell. The D and F's are referred to as inner electrons because they're never ever going to be filled when the energy level is at the valence shell. And you don't understand this yet, and it's okay. All right, but the only 2 that are ever going to get placed in the valence shell are the S's and the P's. Oh, and the other thing is, guys, electrons don't like each other. That's going to be for later. All right, so when we talk about 3D, sometimes it's hard to imagine that because we're looking at a piece of paper. But what you need to understand is that there are 3 different axes on any graph. Most of the time we only deal with the X and the Y. But the Z axis is going to be that 3rd dimension. In chemistry, for some reason, they changed the letters. It doesn't really matter. But there's an X axis, there's a Y axis, and a Z axis. Excuse me, the nucleus is right square at the intersection of all 3 of those. And so everything that we're doing is 3-dimensional. All right, So, electron arrangement. Why are we even doing this? Because guys, everything about the arrangement of the electrons tells us what atoms can do. It deals with chemical reactivity every single day, since it's the electrons that are being shared or they're being lost and gained. So it's really important for the remainder of the year. All right, so what I want to do is this. I'm going to show you some things, but what I want you to look at is these notes kind of off to the side. I need you to see this. This is going to work kind of as a progression. And then there's another slide that'll do this, but in between these two slides, I want to go ahead and have you answer at least one more question. So look at this s orbital. It's a sphere. It's really, really tiny because it's the 1s, and it can hold a maximum of 2 electrons. All right, and you can see those 2 electrons. I just placed them in there. All right, so once that's filled, the next thing that happens is the 2s orbital comes in. It's also a sphere. The only difference between it and the 1s is that it's bigger. It still can only hold 2 electrons. All right, so what happens when the 2s orbital is filled? Well, then we go to what is referred to as the 2p's. But they have a special way of filling. So I need to spend just a second or two to show you what the p's are. We call this a peanut shape because you see the bulbs at both ends, and a peanut, like in the, like a regular peanut. It has the nuts, and then it's got a center that's kind of compressed. All right, so what you need to understand is each one of these 3 colored orbitals is actually referred to as a suborbital. Each of those colors, the blue, the pink, and the green, can hold a maximum of 2 electrons. All right, there's the 2 X, there's the Y, and there's a Z. Again, this is the chemistry version. So guys, if each one of those can hold 2, think about how many the entire set can hold. All right, so remember a few slides back, I suggested electrons don't like each other. Why? Why wouldn't electrons like each other? I think each and every one of you guys know that the whole idea is opposites attract, likes repel, right? They're all negatively charged. Given a chance, they're going to stay as far away from each other as possible, which is why all of the P's have a very special way of filling, and that's what we're going to talk about now. It's known as Hund's rule. Okay, Hund's rule is also known as the halfway rule. It says, and I'm reading this to you, I'm sorry, but it says each suborbital that has the same number and shape. Okay, so you got 2p, 2p, 2p. The only thing different is whether it was the pink, the yellow, green, or the blue. That's it, which is their orientation. They're the same shape and size. So what it says is each one of those has to have 1 electron before any of them can have a second one. It's also referred to as the monopoly rule. And if you've ever played Monopoly, you know that when you have all the houses on a street or whatever its area is called, you put one house on one place. You can't put a second house on the same place, like Park Place, unless Boardwalk has a house. Once you both have a house in both of them, then guess what? You can add a second house. And then you can add a second house. And in this particular case for electrons, the maximum number of houses you can have is 2. We're talking about electrons, though. All right, so let's go back to adding electrons to those 2p orbitals. So using Hund's rule, this is the px. I'm going to put an electron in the px orbital. Hund's rule says I can't put one in the other side. So what do I have to do? I'm going to go to the 2pz, and I'm going to put an electron in there. I still have one more shape to put something in. So guess what? I now have the py, and I'm going to put one in the py. Now that I have one in each of these, guys, I can put in the last three. Right? And at this point now, each of these orbitals have 2 electrons, and they are filled. And once they are filled, then what we have to do is we have to move on to the next level. All right. So there is a second rule. We talked about this kind of at the very beginning, and I said we were going to look at it later. And this is known as Aufbau's rule. It just basically says the electrons have to fill the lowest, and I should have used the word energy orbital available. So what we're going to do, and we'll learn a lot more about this when I get back, we're going to talk about the idea that energy levels have 2 parts to them. They got the number, which is the row, and they have the shape. Put them together and you get energy levels. All right, so 1s, because it's the smallest and it's the simplest shape, is the lowest energy level. Just very simply, that's the way it works, okay? 2s is the second one. It's bigger, it's still an S, but it's at energy level 2. So 2 is bigger than 1, but the S's are the same. Right after the 2 S's, we go to the 2 P's. And why do we do the 2 P's? Because they're still at the same energy level. They're still about the same, that circle's the same, but P's are a more complicated shape. So that means they have more energy. Once the 2 P's are finished, and if you just go walk your fingers across periodic table, you're going to say, okay, look, I only got one thing. I'm going all the way to the end of the 2's. And when I get done with the end of the 2's, guess what I'm going to have to do? I'm going to have to fill the 3's. And the 3s orbital, okay, the 3s orbital is just like the 1s and the 2s. It's just bigger. We still can only hold, it's still a sphere, we can still only hold 2 electrons. All right. And you see everybody's stuck inside of there. All right, so putting it all back together. This is just a way of being able to see it. There's your S's. At the next level of energy, you've got your 2 P's, then you're going to have your 3 S's. And what you see is you started at the bottom, and so you went up a row, then you had to go up another row and kind of filled in all 3 of those, and then up. This is known as Aufbau's filling. You're going to learn this graphic really, really well, but for right this very second, you don't need to spend a whole lot of time with this. All right. Last slide, guys. Last slide is just a summary of the orbitals. We had the single s orbital. We have the p orbital that has 3 different orientations. It's just because, guess what? There are 3 dimensions. You got to cover every dimension. All right, I'd like you to look at the D's. The D's are different. These are, again, the daisies, double daisies. Notice how many there are. There are 5 of them. Then what I'd like you to do is just take a second and count how many boxes there are in that middle section in between the representative elements. That it's that middle horizontal area, not rows 1 or 2, not rows 13 through 15 or through 18, but basically the rows 3 through 12. Count how many boxes there are. Each one of these shapes can hold 2 electrons. Does it match the number of boxes? And then the last one is this. You got 7 f orbitals. And each of these 7 f orbitals can hold 2 electrons, which is 14. These are the ones found at the bottom of the periodic table. All right. So guys, it took me 22 minutes or 20 minutes to go through this. Thank you very much. I will be talking to you later. Get this Ed puzzle filled out for me. And I will see you when I return. Okay? Thanks, guys.